Okay, we'll go ahead and get rolling here. Next, we're going to hear from the François Tissot Group. This group actually had two independent projects going over the course of SRC this summer. And the first part of that group, we'll hear from mentor Shane Houchin and Eddie Ramirez.
Hello. This one here. Hello.
It's working. Hi.
Hello, my name is Eddie Ramirez. I'm a SRC student. My mentor was Shane Houchin, and today I'll be talking about my journey of the sample collection and preparation of the San Gabriel northosite, where I involved breaking, crushing, and some melting. So what is the San Gabriel northosite? Well, it's a Proterozoic massif type northosite, which kind of sounds like confusing, so let me just real quickly explain you those words. A Proterozoic is Earth's middle age, from 2,500 to 540 million years ago. And a massif is a large dome-shaped body of rock, and a northosite is a platonic igneous rock composed almost entirely of plagioclase. And if you see this image right here, that's the plagioclase, which is the gray and blue, which is mostly what this rock is made out of. These rocks only formed from 2,600 to 500 million years ago, indicating that unique conditions existed on Earth at that time. How and in what geologic setting this particular type of rock form has been a long-standing debate in geology. Even though among the debate, there has been, this is what's mostly agreed upon about how this northosite really formed. And in A, magma is accumulating in the deep crust, and then there's iron and magnesium rich minerals crystallizing first, and then sink. And then in C, plagioclase is less dense, and then the melt, and then it floats to the top. And in D, the plagioclase accumulates and begins to rise into the crust, where then in E, the northosite is eventually in place in the mid-upper crust. So one of the big major questions we focused on, in what geologic setting do the massif type of northosite kind of form in? So one of the type is the divergent margin, which is two plates being kind of pulled apart. And then the other one is the convergent margin, where two plates are kind of going together and colliding. Previous work shows that northosite complexes can be extraordinarily long-lived. In this image here, this is an image from a northosite complex in West Africa. And these researchers measured uranium and lead in zircon crystals to determine their age. And zircon, by the way, is a type of mineral that is considered the gold standard of radiometric dating. So what they found here in the image is that the oldest zircon age is 1,500 million years ago, and the youngest is 1,320 million years ago, indicating crystallization occurred over 180 million years. And this is a long time even in geologic terms. So here's our second question is, did the San Gabriel northosite form over a similarity long time period? Here are the methods we're going to use for each of the questions we just went by on the past slides right now. For question one, it's whole rock geochemistry. And for question two is uranium and lead geochronology of zircon from the San Gabriel northosite. But we mainly focused on question one. That's what we mainly did during the program. Now let me get into more of my personal experience and my contribution to this project. So field collecting. Me and Shane and his friend Juan went to the San Gabriel Mountains, where we went to a outcrop where we collected rocks. So we tried to collect the type of rocks that were less altered and more fresh. And when we were there was this bug that, I don't know why, but he just had a problem with me, so he bit me a lot of times. I don't know what he wanted with me, man. And after we finished collecting and the bug was no longer in my problems, we went to this pretty good chicken place, which was really good, and I felt rewarded, and I felt like all those bites were worth it. So then we brought it back into the crushing room, where then we put it into this jawbreaker, which then we crushed all the rocks into a powder. So what do you do after that? Well, you make it into even more powder because, you know, why not? After we made it into even like finer powder, we then measured it before we put it into the furnace. And after we took it out of the furnace, we measured again to see how much of the water that was inside the minerals was burnt away. And here, this is where I was taking the samples that just got out of the furnace kind of, and little kind of breaking it apart because after it came out of the furnace, some of the samples were like sticking together. So I had to break it apart, which then I weighed it to a very precise number. And I know I shouldn't say this, but I got like 3 in a row, which was the exact price number. So I was really happy. And then we also added together with a flux, which made it just melt more and just better into the furnace right there. But sadly, the X-ray fluorescence has no chill. So the whole rock data is coming soon. And sadly, the chill for the machine wasn't working, so we couldn't get any of the data, sadly. Sorry. Here are my key takeaways that from this program. I learned the fundamentals of geology, and I gained a understanding of the local geology of the San Gabriel Mountains. I gained experience collecting samples in the field and preparing samples in the lab. And in all honesty, I think geology is pretty cool. So, yay. That's the end of my... No questions, please.
Which chicken place?
I forgot his name. What was his name again?
El Pollo Pio Pio in Kahanga.
Oh,
It's really good.
So that was my next question. I was going to ask if you went at the top of Lake up into the San Gabriels, but you went over to.
We went. It's up Big Tahunga Canyon near Monte Cristo Campground where we collected.
All right, more geology in your future?
Maybe.
Maybe.
Pretty cool.
I had a sampling of astronomy with us last year with the Planet Finder Academy, and now geology. Any other questions? We have several Planet Finder Academy alums or current students here in the rooms. We're glad you're taking advantage of these programs. Any comments, Shane? Yeah.
Yeah, I mean, it was really fun going out in the field. I like talking about rocks. It was nice to take someone out there, and yeah, Eddie did just a great job with all the sample preparation. Yeah, unfortunately, as he said, the XRF, the chiller went down just this last week, kind of right when we were about ready to run the samples. So that data will be coming soon. And all of the crushing that was done as well will be helpful for the next stages of the project when we start trying to separate zircons. So it's a big help to have Eddie here.
Hi everyone, I'm Matt, and I'll be talking about what we've been doing in the Tissot lab this summer. So a little bit about the project. We're looking at meteorites and trying to determine their age. That's really important. It gives us so much information about the formation of the solar system and kind of the processes that led to what it is today. Cosmochemistry is the study of blah, blah, blah. More specifically, it's isotope cosmochemistry. That's the field name. It has many applications. Not only the age, we also have to look at the composition of the meteorites. That really tells us a lot. And the process of dating meteorites is pretty complicated, but it's really worth it in the end. It gives us really valuable information. So that's what we've been doing. A little bit more in depth on the process. First, when we get a meteorite and we need to dissolve it and get it into a liquid sample, that's much easier to handle. After that, we put it into the machine. There's like a little tray on the right of the machine there. And then the machine takes it up from there. That's the inside of the mass spectrometer. Sample goes in here, turned into an aerosol, and then it's carried to a plasma torch. Right here, plasma torch. It's very, very hot. So it turns our sample into a plasma-like state and ionizes the atoms in our sample. And it's carried all the way to the crush bowl. and it's filtered and separated our atoms, and then from there they reach the detector where the computer gives us the data. We need to then combine the data because there's some biases. So there's so many components in the machine that every single one has a little bit of error attached to it. So these are a couple of the methods that we use: double spike, SSD, regression. Most of them have the same principle of measuring materials that we know the composition of them, and we know the ratios. So when the machine gives us a value for that, we see that it's a little bit off, and from that we can correct our data. After we get our corrected data, we use an equation to determine the age. This is one that we use very often. It involves uranium-235 and uranium-238. We put our values into that, and it's really nice. It gives us the age. Another really, really important part of the research is the clean lab. It's very clean. What can I say? I mean, that might seem very self-intuitive, but it's really clean. You need to wear so much gear: the lab coat, the hairnets, the gloves, and the really comfortable Crocs. These are two different types of acids. There are more, but we use those typically to clean everything about 10 different times. It takes a lot of time. It's pretty, but we need to do this to get the most accurate results. Also, in the clean lab, we do something called the column chromatography. Basically, we filter our sample through the resin, we call it. It's a hard part of the column. And we make it go at different speeds, which gives us different mixtures of our elements so that we get the ones we want. In this step, you can see there's a little bit of liquid. That is the acid again, because we have to clean it. And the brown part is the resin, actually. And after we're done cleaning it, we put our sample through it and we get our mixture. Now, finally, last thing I want to talk about, this is the most important skill I got out of this whole experience. The research papers. They're very long, very long. First, when I just started reading them, I didn't understand anything. It was reading gibberish. And then had to read it 3 times. And then I started to get an idea of what it was talking about. These are just a couple of the ones that we read. But in the end, I think now I can read a paper and understand mostly what it's talking about. And this is such a valuable skill. So that was the most important. Thank you, Mitch, and Some Research Connection for facilitating this. And thank you, Haoyu, for being such an amazing mentor. Thank you, everyone, for listening.
Haoyu, any comments?
So I think you did a wonderful job. You have a lab this summer, understand all the things very quickly, and then it's also very quick. I'm very proud of the presentation and outcome of this program.
Thank you. Any questions?
Yes. Yes. That's right. No questions. Okay.
So you were working with, did you say meteors, right?
Meteorites.
Meteorites. So you obviously didn't go collect them. They're existing here at Caltech, and is that you're doing ongoing work with that same set of meteorites?
Yeah. So this especially like the concentration measurement with mass and the chromatography. We will run another mass session, but so they are happy to have all. Yeah, we are working.
Any other questions? Thank you.